everybody. I think we're ready to start. We're very lucky today. I'm going to introduce you. We're going to start our speaker very soon. So I'm very fortunate to introduce you Kotresh and Wei Hang. They're both from Walmart Lab, and they are going to give us a wonderful talk, and they're going to introduce you and tell us more about themselves.
Sure. Hey everyone, this is Yash. I've been with Walmart Labs for 2 years. I'm a data scientist there. This is my first event for the Kotresh, and I'm actually excited to be here. I feel very safe here, and I'm looking forward to give my presentation. I'll just ask Wei to introduce herself.
Hi, yes, Wei. So I'm also in Walmart Labs for 2 years. I'm a data scientist there. Worked in the search team. We're very happy to get the chance to present our project here.
Okay, let me start. So today's presentation is actually, the topic of my presentation is item discoverability in search. And the flow of the presentation is going to be the background and the use cases. Today I'll be talking about a machine learning system we use in the search to provide recommendations for making items discoverable. And the methodology will talk about modeling piece using machine learning, validation, and then we will be talking in depth about how we plug the system in search and then how we evaluate the results. So one of the key components of any search engine is to match customers' demand. In e-commerce context, it is like a customer expresses his or her demand through search query, and we want to make sure that we provide the most relevant items, preferably on the first page result. Let me illustrate my point here. So when I went to walmart.com, I entered this query dining table set, and I got this result on the first page. It was interesting, it was good, but I wasn't very satisfied. So I moved on, and actually I finalized a product in page 2, position 3. And this item has the potential to be on the first page, but because it was introduced newly, so it couldn't get into the first page. So the idea of this project was to identify those items which have the demand to be on the first page, and I would address them as non-discoverable or yet to be discoverable items. And the way we would recommend this item is they should have attributes very similar to the most demanding and trending items. So why would any search engine want to take the risk of providing information about not discovered items? One is, of course, to understand the customer demands, to understand what is the potential demand of the items we ingest every day. And that could be done by introducing the diversity of items. And of course, from the user experience perspective, we'll have better choices of items providing to the customers. And the second is, of course, which would, to increase the number of unique SKUs sold. This is one of the business need. One of the other use case where we can actually extend our machine learning system is in providing recommendation to our suppliers on ingesting new items. On walmart.com, we ingest like thousands of items every day, and we have to make sure that we prioritize based on the demand from the customer. And the key assumption here is that the demand, since we are analyzing from the query set, it is very comparable in the future as well. So this is the entire overview of the whole machine learning platform we are using at Walmart Labs. So we look at the historical data for the performing items. So we look at our catalog and divide it between two things. One is performing items, the other is non-discoverable items. So for the performance data, we look and we feed it into our learning model, machine learning model, and then we learn the model of the performing items. And then we use the model on the non-discoverable items, and then we get the performance of if they had made discoverable, what could be the potential demand for them. And then we would look at the metric and plug it into our search system. So we go through the entire recommendation, cost opportunity analysis, and evaluation. So the first step is how do we define which items in my current catalog be differentiated between discoverable and non-discoverable. So one thing I wanted to make clear is that the demand for customers come through different channels. One is search, browse, ads, but right now we are just focusing on the customer search experience. And the way we differentiate an item as a non-discoverable item is when we look at that they have less than T impressions in the last K months. And the absolute value for all these parameters would usually come through looking at the historical data, and you want to analyze, you probably want to plot something like this to understand what's the trade-off between the search volume and the positive events of the metric you're using. So for me, for us, it's been the event we evaluate is the add to cart. When a customer goes and selects a product and add to cart, that's the event for us. And then based on the analysis, we'll come up with the values for T and K. So the next piece is we are able to now differentiate what are the items are discoverable and what are the performing items. The next step is to learn the performance of the performing items. What are the attributes which are contributing to its performance? So the potential features we can use in our machine learning model are the product attributes and values, like metadata coming from the products. We can also use the price, the competitive price, and now we have sophisticated techniques to even use images. So these are the potential features which can go into our model, learning model. So, and the modules we tried is mostly logistic regression, and we use different actually different libraries, and wanted to actually, biggest problem for us is scaling this product. We do our analysis at the query level, and one day itself we have millions of rows. So for us was paralyzing the entire, it's actually a big data when I'm talking about it. So we wanted to paralyze this entire exercise. For us, the training should take like at least 3-4 hours rather than training for days. So instead of, so there are two ways to paralyze this this whole learning model. One was to paralyze on the hyperparameter, which is learning what are the parameters we should have in our learning model, and the second is to paralyze on the data itself. So we actually experimented with all of these using logistic regression. SGD classifier is a part of a logistic regression, but they use another optimization technique, it's called stochastic gradient descent. So we used all this, and finally we narrowed down that we were able to do well with the scikit-learn using logistic regression with weights, and we were better parallelizing the hyperparameter than on the data. So we use this to implement our model. So the next thing is, how do we validate? Once we have the training, we need to make sure that we are validating on a test set. So one thing, if I look just on a day's worth of data, there's a lot of seasonality and trend associated with the data for it to go into our testing. We won't get the good accuracy numbers. So the idea here is to choose a time frame which is sufficient enough to give us decent accuracy. Like for example, here the algorithm I followed for validation is I chose a time frame which is good, which is long enough for us to capture all the seasonality and trend. And so for example, here I took a week worth of data for my testing, and then I created bootstrap samples. So bootstrap is a very well-known technique of reducing noise and also variance in the data. So I had like n number of bootstrap samples. Then I made prediction on those samples and then got the accuracy numbers for them. And this is a plot which shows what is the accuracy number for that. So I have like n samples, and this is like for those n samples, what are my range of accuracy. So as you see, as we keep increasing our time frame, we could see that the accuracy is actually between 5%. But we want to make sure that we have a trade-off. We can't wait for a whole year to validate our data. So the time frame is like, I think here for the graph it's 2 weeks, and we could say that 80% of my data is actually within 20% of accuracy. So this was the validation step. So the next, once we have our model, we learned our model, we validated it, and we got good results of the model, we want to plug it in our search to make sure that it goes as a signal for discovering new items. So that will be taken care by Way.
Thank you, Yash, for talk about the background of the product and how to build the model. Here I'm going to talk about how we are going to use this model. So first I will talk about how we use the model in search. So in search, given any query, it will return a set of items with the original scores. The original score is mainly capture the relevance between the query and the item. As Yash has been discussed, this score will be biased against new items, which means for two similar items, the new items tends to have a lower score. Then the new items tends to be ranked lower and become less discoverable. So we are going to add some boost to adjust the bias. Here are several rules we will use to correct the bias, to add the boost factor. So first, we only add boost to non-discoverable item. If one item has already been discoverable, we're not going to add the boost. Then the second rule is based on the relevance. So we only apply boost factors to relevant items. If item is not what the customer looking for, we're not going to put this item on a higher position than the item that customers are looking for, even the item have a higher add to cart estimation. Then the third rule is the boost factor is correlated with the add to cart estimation. If the item have a higher add to cart estimation, then we will give it a higher score. Let's take a look at this example. So a customer is searching for a 50-inch TV. Here are three items retrieved by the search engine with the original score of 1.7, 1.4, and 1.2. Let's check these three items. First, the first item has been purchased a lot and is discoverable, while the second and the third item are not discoverable. We're not going to add boost to the first item. Next, let's check about the second and the third item. The customer is looking for a 50-inch TV, while the second item is a 58-inch TV. The size of the TV customer looking for is different from the size of the TV of the second item. So we're not going to add the boost to this item. Then for the third item, this item is non-discoverable and relevant. Then we are going to add boost to this item. Here the score, the boost factor we add is 0.7. Then we get the final score. The final score is the sum of the original score and the boost. Then we get the final score, and the final precision is based on the final score. After adding the boost factor, the third item will be boosted to the first precision. Then this item or more customer will be able to see this item, and this item could accumulate more impressions. Then the bias against new item will disappear for this item. This is one static method. We can also have some stochastic methods. So multi-arm contextual bandit is a framework that naturally tackles the discoverability problem. So there are two aspects of a multi-arm bandit framework. One is exploitation, another is exploration. Exploitation refers to optimize the search engine based on the existing search result. Like in our situation, which means we show items that has been performed very good in the history. Exploration is to show items that to acquire new knowledge. Which means like we have some items that potentially good but not historical good, then we can show these items to customers to test whether the customer really like this item or not. The multi-arm bandit framework balance this exploitation and the exploration, and to maximize the total value. However, you can imagine if there are only a small set of items, then the learning process could be very fast. But if there are lots of items, then the learning process will be very slow. So the main challenge we are facing is we have really, if given these millions of items, then the learning time is very long. Then we are putting our customer experience and revenue at risk. But add to cart estimation is here could help us serve as a prior knowledge to speed up the learning process. So we can do more exploration on items that have higher add to cart estimation. Then it can help us avoid making more mistakes. Now we talk about how we use the add to cart estimation. After we build this search relevance feature, next step is to evaluate the feature and then to launch the feature. So we follow the industry standards to evaluate and launch a relevance feature. For example, we have in-house evaluation team to calculate the relevance score. We also conduct the evaluations through cross-sourcing. Finally, we always do A/B testing to evaluate our search features to get the idea of the impact on the whole website. But here I'm not going to talk about this. I'm only going to talk about two things that is special to this project. First thing I was going to talk about is the search engine comparison based on the aggregate estimation at cart. So here are two search engines. One is the old one, one is the new one. Then for each of them, you can get a list of items, and then you can get the add to cart estimation for each of these items. You aggregate this score, then you will get a cumulative aggregate estimate add to cart. So we compare these two scores and to see which one is better. So in this example, the new search engine is better for this query, and the aggregate estimate at cart rate is higher. What we are doing for the engine comparison is we not like look this by eyes, like one query by query. We build our tools to crawl a set of queries. We generate a representative sample of such queries, and then our tools will automatically crawl the results for this set of queries, and then we can get a report to say, okay, on which set of queries we have better add to cart estimation, which set of queries we have worse add to cart estimation. And this method is very low cost and fast feedback. It helps us during the development period of time, so we can quickly identify the issue and go back to the next round of development. Another thing we are using special to this project is SEO index. We use SEO index to quantify the diversity of items presented to the consumers over queries. SEO index is a concept from economics. So they use the SEO index to quantify the economic equality. Now we use this to quantify whether the impressions is distributed over items equally. So we long-term monitor this, use dashboard tools to make sure like our discoverability project is healthy over time. Okay, any questions?
I have a couple of questions. So when you said item discoverability, how do you determine whether an item is discoverable in the first place?
So actually this whole talk was about that. So one of the things is that actually if there's a whole system we have which is more scientifically designed to make sure that and validated to make sure that we get the best products to make items discoverable. But if I just have to give an overview, the system actually identify the items which are very much similar to the trending and demanding items. Their costs are comparable, the attributes they have share with the demanding items. So that would usually surface out to be made discoverable. So they would have not been discovered because they were newly introduced, they didn't have many clicks, or there were not many conversions, so they were newly introduced. So the idea is to put them forward so that it can meet the potential demand from the customers.
Right. So how do you determine that this item needs a boost? Like, is because not enough people have clicked on it over time?
Yes, so exactly. So when I say that, this is the slide where I say that, okay, we differentiate how do we find out which items are discoverable and which are not. That is, we look at the impressions. So if it is less than T impressions, we would say, okay, these items are not being discovered. Once we classify them, we put it in our system.
Sorry, what is an impression?
Search impression. So whenever a customer,
Search results?
yes, yeah, that's a search result. So when we are able to classify those items, we look at the non-discoverable items, and then it goes to a machine learning system, and then it will identify which are the items we could potentially boost them, and also give us what are the quantities we can boost on.
Okay, and then my second question was the comparison, the old cart and the new cart. Yeah, that was in your slides. And you say this one's better than this one. How do we know, like, this one's better than that one? Are you going off the total estimation? Like, if the estimation cost is higher, then it's considered better?
Yes. So this score is the probability, like customer adds this item to cart. So if the score is higher, that means it's higher probability the customer adds to cart. Yeah.
Okay.
Yes. Yeah.
Yeah, I have the same question. I was wondering, how are you exactly, determining which search engine was better? Because the first product that's given by the new search engine is 49-inch, but in the previous slide that Yash was showing, 58-inch was was given the second boost because it's not meeting the search criteria. But here the 49 was given the first priority, and then the second and the third. So when you say the new engine is better, is it because the very first item was given more cart ads?
Yes. So and for this add to cart estimation, it's what Yash has described. We learned this from the machine learning model. So then we learned this like through the similarity of attributes between like the new item and the good performing items with enough history. So this score are learned from the model, but all those numbers and screenshots just for illustration, like it's not like really the score. Yeah. Okay.
So how do you determine the boost effect?
Oh, that's a good question. This is it's a very important process in our search engine. So if you have like really, so this is also like trade-off between exploration and exploitation. If you have a really higher boost, then to go to the end of lots of exploration. If you have very lower boost, then you don't have enough effect. You go to the end of exploitation. So there are some trade-off, and we do have those kind of evaluation system to help us find the best trade-off. Yeah.
And also the accuracy used, I'm sorry.
Yeah.
Sure.
You said 80% of your items were meeting 20% of the accuracy.
Yes,
and that data was from the 2 weeks of...
So that is something you can play around. We can't give you much details, but it's like a time frame. You choose, okay, a week, and then we see the add to carts, and we observe the add to carts, and that would be our test sample. And then because we are limited with the data we have, then we create the bootstrap samples, which you know the technique of bootstrap. It's like sampling with replacement, and we create samples so that we can reduce the noise. And then we know what's the true value of the add to carts or whatever the metric we have, and then we compare how are my predicted versus observed, and that's the accuracy number we get. So the idea here is that, as you can see, these are the all the green plus the blue are the total samples we have created in that time frame. So you can play around with, if you have a system, you can play around with the time frame and see that how the data is getting aggregated. Usually, as we increase the time frame, we have seen that our accuracies get better, but it is very tough. If we implement this in our system, we can't wait for 1 year to find the accuracy. We would say, okay, let's gather the 2 weeks and see how our model is performing. You had a question?
Yeah, I kind of had the same question. How do you trade off between the accuracy that you want for your model versus the time it takes? So how do you determine that, okay, in 1 week I'm getting, let's say, 50% accuracy, so it's good enough for me, I can just use this model? Or do you say, okay, I can train it for a longer period, let's say 2 weeks, then I might get, let's say, 60% accuracy, that's better?
Yes, so I agree with that. So this is more like of a trade-off analysis. And this, usually we have stakeholders with whom we work with. So we come up with the accuracy. Usually people are, when we have machine learning systems, at least with the ones I've played around, the accuracy we want is 80 to 90. 100% is over ambitious and you don't want the system to learn everything. That's the ballpark number. And the time frame, when we have to choose, we want to make sure that it's a lot narrower, because the idea is to productionalize the system. Once we productionalize, we want to evaluate how our model is doing. If we take a time frame of 6 months and say it is giving 90% accuracy, we can't wait for 6 months to evaluate our model. So we want to have the much narrower time frame and get the better accuracy. Anybody? Okay. If you guys have any questions, just grab us outside. Thank you.